All right, guys, so we're going to do 2.3 today. I decided to switch 2.2 and 2.3. We'll do 2.2 next week, just on the off chance it does take more than one day to get through it. Now, 2.1 wasn't too bad. 2.3, again, is not that bad. It's not anything brand new that we're going to cover, because the first thing we're talking about is a relation. A set of ordered pairs, so x, y, is called a relation, where we just have a set of numbers, where it's not a function itself. We don't have it as y equals or f of x equals. It's called a relation, where the x values in the ordered pair of the domain, the values we plug in, are x values, and the y values are our range, output. To where if we looked at this here, we have a set of information, x and y, hours of study and test scores, shown here. So shows the scores y that a student earned on an algebra test grade based off the number of hours spent studying 1 week prior to the test. So if we wanted to write these ordered pairs as a relation, we would connect the x and y together. So we'd have 8, 92. We'd have 3, 58. We'd have 11, 98. 5, 72. And then we'd have 8, 86. So this here would be the relation, the x and y values in their ordered pairs. Now, if we talk about the domain, again, we're just talking about the x values. So we'd use a brace and list out the domain values. And we could list them in order. So the first one that we have is 3. Then we have 5. Then the next one we have is 8. Now, even though 8 shows up twice, we only have to list it once. We never have to repeat any of the numbers. And then the last one we have is 11. So those are the domain values, the x values, the input values, if we're talking about a function. And the range is the output values, or the y values. So we can list them out. So brace. First one we can list is 58. Then we can say 72, 86, 92, and then 98. And that's it. Questions on this here? It's been a little while since you've done these, especially with relations and just listing domain and range. Now, definition of a function. Given a relation in x and y, we can say that y is a function of f if for each value of x in the domain, there's exactly one value in the range, 1 to 1. Another way we test functions is with the vertical line test. If we can draw a vertical line anywhere on the graph and it crosses more than once, it's not a function. And really with function notation, to state it as simply as possible, if there's anything attached to y, it's other than a number being multiplied in front, most likely it's not going to be a function. So we're talking about having stuff like y squared or y cubed, y to any power. Or we take the absolute value of y. Or we have x times y, or the square root of y. There's a good chance it's not going to be a function. Now, we want to determine if the relations defined as y are a function. So if we look at A, can we say that A is a function? Yes or no? Well, let's just go on and list out the domain values. We have -4, -1, 2, 3. Yes? Those are all the domain values. All the range values we have are, so you're -4, 0, 1, 2, 5. And I'm doing a map. A mapping is just taking the domain and range, set them next to each other, and drawing arrows connecting them. So we know 3 is connected to 1. 2 is connected to 5. -4 is connected to 2. -1 is connected to 0. And 3 is connected to -4. Do we have one x value for every y? No. Three is going to 2 different points, yes? So if we were to graph this, at 3, we would have a spot at -4. And at 3, we would also have a spot at 1. We have 2 x values, 2 points that are making a vertical line. This is not a function. We can have 2 different x values going to the same y. We cannot have one x value going to 2 different y's. So we can have 2x for 1 y. We can't have 1x for 2 y's. So this here is not a function. Now if we look at b, the x values are -1, 2, 3, -4, and yes, they are out of order. The y values are 4, 3, 5, because we had 4 twice. So -1 is going to 4, 2 is going to 3, 3 is going to 4, and -4 is going to 5. And even if we looked at this graphically, this is still a function. Because at -4, we have 5. At -1, we have 4. At 2, we have 3. At 3, we have 4. And that's it. Do any of these points, can we draw a vertical line through more than 2 of them? Or 2 or more of them? No. So is this a function? Yeah. This one is a function. That's it. So if you're not sure, go on and graph the points and see, do they line up? Do 2 of them line up? Because we can have 2 different x values going to the same y. We cannot have one x value going to 2 different y values. Determine if the given relation defines a function, if it is a function. So what would we say? A, is that a function? No. And we know it's not a function because it does not pass the vertical line test. How about letter B? Yes. Hopefully we should recognize B, that is a quadratic function. At least it displays what a quadratic function should look like on our interval. How about letter C, or the last one? No. Is if we draw a vertical line, everywhere here it's good, yes? And everywhere over here it's good. How many times does it cross when x is -2? Twice, because we have 2 closed circles. So this would be no. This is no. Now, if one of these 2 or both of these 2 points had been open, then we could say yes. Or if the top one was closed and the bottom one's open, then it's yes. Because when we have an open circle, it means it's not equal to it at that point. So it's jumping to the other one. We'd only have one at that location, or none if they were both open. Does that make sense? Okay. Again, yes, no. For letter A, this mapping, can we say it's a function? Yes, because we can have two different x values going to the same y. We can't have one x value going to two different y's. How about letter B? Is y squared equal to x a function? What do we think? No. One of the easy ways I could say that we can determine if it's a function or not is trying to plug it into the graphing calculator, because I can't plug y squared equals x into the graphing calculator. I mean, we could. I could take square root of both sides, which will tell me that y is equal to plus or minus the square root of x, yes? And I could graph it. Let's see how long it takes to pull this up. So y equals second square root x. Well, we also have to take second negative second square root x, graph. That's definitely not a function. And if you have to put it in two separate spots in the graphing calculator, most likely not going to be a function. So this here is no. How about C? What do we think? Is this a function? Yes, no. Does anybody know what that equation's for? It's a circle, so this is no. It's the equation of a circle with center 2, -1 with a radius of 3. So no, this isn't a function. And again, one of the giveaways is this here. Y has got an exponent. If y has an exponent, most likely this is not going to be a function. The square root one I wrote earlier technically could work, as long as we're not getting to anything too complex. All right. We're ready for some tough stuff here. Evaluate the function defined by g of x for 2x plus 1 for the given values of x. G of -2. Now this is not g times -2. The book actually points this out. I hope at this point we know that that's not the case. G of x, h of x, f of x, any of these are just another way to write y. This is just another way to write y. And we do this because if we're going to talk about more than one function, we need a way to specify which function we're talking about without having to physically point or show what function we're talking about. Because if I said g of x, we know, just looking at this piece of paper, we're talking about 2x plus 1. We know which function we're talking about. I don't have to specifically say 2x plus 1 every single time. And the other nice thing is, so saying g of -2, well, our g of x function, I took x and replaced it with -2, which means on the other side, I'm replacing x with -2. Well, 2 times -2 is -4, plus 1 is -3. That's it. We can do the same thing with g of -1, which would be 2 times -1 plus 1, which is -2 plus 1, which is -1. We're just plugging in those values in for x and simplifying. Anybody have a guess at what g of 0 would be? 1. This would be, it would be 3, and then 5. Because the slope is what? 2. So each time we increase the x by 1, the y is increasing by 2. That's just slope. I mean, an easier way we could have done this is those are all those points. -2, -1, 0, 1, 2. They're all listed out there. Could have graphed it and used the table to find the points. But that's it. We're just plugging the values in for x. Is it possible to do this and get an undefined value? Yes. If we're talking about radicals. We'll do that here in a second. Because if I told you take the square root of 2x minus, make it something ridiculous, 10,000, solve for when x is 0. Is this possible? I mean, it is. We'd have to take the I, because we'd be taking the square root of -10,000. So we'd have terms with I. Or, we can just do an easy one, 5 over x. Solve when x is 0. Is there any way to actually evaluate this at 0? No, so it can be undefined. Literal equations. These here, we're not going to have a specific value because for the first one, f of a, we're replacing x with a. So we'd have 3 times a squared plus 2. Technically, we can put it in parentheses because we're replacing x with a, and a squared is just a squared. That should be 2a. We just replace both x's with a, and it's always a good idea to put them in the parentheses, especially with squares, because if we put a negative a inside the parentheses, negative a squared is positive a, and we get this here. And again, especially with plugging into the graphing calculator or any calculator, it's always good to put parentheses around it, because very easy mistakes are squaring a negative number. If you don't put them, it'll give you the wrong answer. And that one's not bad. That one's actually quite easy. Now, x plus h, we're going to replace x with x plus h. X plus h squared is not going to be x squared plus h squared. I've seen that too many times. We can't just square both of them. If it was x times h, yeah, that's fine. If squaring is just x times h times x times h. It ends up being x squared times h squared. That's fine. But with plus, we're multiplying it by itself. And we've done enough factoring. When I multiply two things together, we get a middle term of their crossing. So we're going to have to multiply that out. Here, just multiply by 2. 2x plus 2h. If we multiply this through, we get x squared plus xh plus xh plus h squared. X squared plus 2xh plus h squared plus 2x plus 2h. Lastly, distribute the 3. 3x squared plus 6xh plus 3h squared plus 2x plus 2h. And that's really as simplified as it gets. There aren't any like terms to combine at this point because 6xh, 2x, and 2h are not the same terms. Because 2x and 2h are different terms in themselves, and 6xh is still a separate term entirely. Questions on this here? done anything that y'all aren't comfortable with doing so far. Finding intercept using function notation. Again, just like we did yesterday, if we want the x-intercept, we plug in 0 for y. If we want the y-intercept, we plug 0 in for x. And it's the same thing with this here. The x-intercepts are all the solutions to the equation f of x equals 0. Set it equal to 0. The y-intercepts are given by f of 0. We plug 0 in for x. And that's it. So if we're looking at this here, the x and y-intercepts of the function is here. So if we want the y-intercept, we're plugging 0 in for x. This here is just 0. So the y-intercept is -4. The x-intercept, 0 is equal to x squared minus 4. Since there is no middle term, we can add 4 to both sides, telling us x squared is equal to 4. Take square root of both sides, telling us x is equal to plus or minus 2. So our x-intercepts are positive -2. The y-intercept is -4. Questions on this here? Determine the domain and range of the function. So domain is just x values, the possible x values that we can have. And really, unless we're talking about square roots or rational expressions, so fractional expressions with variables in the bottom, the domain is going to be all real numbers. For any polynomial function, the domain's all real numbers. Here, we're just looking at points. Not that last one. So we're just looking at the x values for the domain. And we have, the first one is -3, -1, 0, 2, 4. The range is just the y values. So the first one we have is -4. Next one we have is 1. Then we have one at 3, and then we have 2 of them at 4. But we don't have to list 4 twice. We only have to list it once. That's it. Now, it doesn't have to be a set points. We can actually talk about intervals. The domain is over an interval. And if we look at this function and we're looking at what values of x it's covering, it starts at -3, and then it continues on to the right indefinitely. So the domain, there's different ways to write it. So we can say brace x bar. And this is really saying for all real numbers x, such that x is greater than -3. The domain is all real numbers x such that x is greater than -3. We don't say equals to because the circle's open. Now, most likely, it's not going to ask for this. It wants it on interval notation. To our parentheses or brackets. Now, the smallest number in the domain is -3, and it's not included. So we'd say parentheses, -3, comma, infinity, because it continues on to the right indefinitely. And that'd be the domain. The range are our y values. So we'd say for all values y such that, well, the smallest value of y that we have is -2, and it goes up. We would say y is greater than -2. We don't say equals to because it's not included. Or for interval notation, we would say -2, comma, infinity. And it doesn't matter that it plateaus or it stops increasing from here to here. It still includes those points. Questions on this here? The domain for all real numbers x such that x is an element of the real numbers. It's a quadratic. It is literally everything. -infinity to infinity. Well, all the real numbers, not complex. Because we can't plug in I and work for this here. It has to be a real number. The domain is everything. We cover the entire x-axis, -infinity to infinity. There is no real number we can't plug into this function and not get a y value back out. Now the range. This quadratic is opening down, yes? So it has a biggest point, and the biggest point is right here with a y value of 4. So we're saying for all real numbers y such that y is less than or equal to 4. Even though we don't specifically have a dot, a shaded in dot at the y value of 4, it's still included. So we have our less than or equal to. Well, our first number here is going to be what? -infinity, because it is all the values from 4 and down, so the smallest number we can have for this is -infinity. The biggest number we can have is 4, and it's a bracket. Questions on this here? Now, to determine the implied domain of a function defined by y equals f of x, exclude values of x that make the domain of a fraction 0. Exclude values of x that make a radical negative with an even index root. Because again, if we take the square root of a negative number, it's I. It's complex. We can't have it in the real number system. So whatever is going to make the denominator be 0 or a negative inside of a radical. So for most functions, the domain is all real numbers, except when we hit roots with even indexes or fractional exponents. Or not fractional exponents, fractional functions. So if we look at the first one here, we don't have any roots, radicals, but we do have a fraction with a variable in the bottom of it. So here, the domain cannot have whatever value is going to make this negative. Not -0. So, set the thing equal to 0. Plus 5. And solve. So any other value for problem A will work except for 5/2. Yes? So if we want to write this in interval notation for the domain, we would say -infinity to 5/2. Union 5/2 to infinity. And that's the domain. It's really saying everything except for 5/2. Questions on this here? Next one's kind of nice. Because for the next one, x squared plus 4 cannot be 0, yes? So we can set it equal to 0 and solve. So we would subtract 4, telling us that x squared is equal to negative 4, yes? Square root, square root. X is equal to plus or minus. Well, what is the square root of negative 4? It is 2 what? Is that a real number? No. So is there any way I can make the denominator 0? No. So the domain is all real numbers. Because we've gotten very used to the fact that if we have a fraction, there is some real number that can make the domain 0. We don't normally talk about the fact that, well, it doesn't have to be. We could have one like this here where there is no number that would make the denominator be 0. So the domain's still all real numbers, because there's no way to make x squared plus 4 be 0. Questions on this here so far? Okay. The next one's a radical. With a radical, these even roots, what's inside the radical cannot be negative. We can't finish out with a negative. So what we're saying is that 2 minus t has to be what? Greater than or equal to 0. Because can we take the square root of 0? Because the number times itself that 0 is 0. 0 times 0 is 0. We can have it. Inside this radical can be 0. It just can't be less than it. So we get minus 2 from both sides, telling us that negative t is greater than or equal to negative 2. Divide by negative 1, telling us that t is less than or equal to 2. So any number less than or equal to 2 will give us a solution, which means the smallest number in the domain that we can have is actually negative infinity. The biggest number we can have is 2, but we do need a bracket because 2 is included. Because 2 minus 2 is 0, we can still take the square root of 0, so that is the domain. Now luckily with most square roots, we can graph it. Second square root, 2 minus x. Graph. And we can see here on the x-axis it stops at 2, yes? So it's negative infinity to 2, all those x values. Because anything bigger than that, if we look at the table, it's just going to tell you it's got an error. It doesn't work. Questions on this here? I like the fact they threw the last one in, the absolute value of 4 plus a. Because with absolute values, we know it cannot equal a negative. We can't have it equal a negative number, yes? Are there any restrictions on what I can plug in for a? No, we can plug any number we want in for a. So what's its domain? All real numbers. Value, I think it was 4 plus a. Covers the whole x-axis. All real numbers. Because again, the only ones that we're going to really have restrictions are when x is in the bottom of a fraction or inside an even root. Those are the times that we're going to have a restriction. Find the domain of this function. Write your answer in interval or union of intervals notation. Well, we have two things. One, the radical in the numerator can't have a negative number. So we're saying that x plus 8 has to be greater than or equal to 0. X is greater than or equal to -8. And we're also saying the denominator, 2x plus 8, cannot be 0. Minus 8 from both sides, telling us negative 2x is equal to -8. Divide by -2, and x is equal to 4. Questions on this so far? So far all we've said is that x has to be bigger than -8. So, bracket -8, comma. So anything less than -8 is not going to work. So what's the next biggest number we can get to? Because we can't just go to infinity, we also have what? Can't equal 4, right? So we have negative infinity, -8, comma, 4, parentheses. We have to put a parentheses because that would cause a division of 0. We can't have it. At the union of 4, comma, infinity. That'd be it. Questions on this here? And yes, the domains can get kind of funky the more that we do this. Because if we talked about this function here, well, what's going to make the denominator 0 is when x is 2 or -2. Because those are the two spots where x is going to be 0. So that means the domain for this function is going to be negative infinity, comma, -2. At the union of -2, comma, 2. At the union of 2, comma, infinity. Because we have to pull out both of those numbers, but everything else works. Does that make sense? For each number that we pull out for a 0 in the denominator, we have to exclude it from the interval, which means we keep having to do chunks of the interval, or chunks of these unions. It would be nice if they would let you do this, especially in the homework, to say all real numbers except points 2 and -2. That is technically a way to write it, but they're going to want you to do it the other way. And this is it. This is the last part of our chapter. Use the piecewise function f, or use the function f pictured to answer the question. Determine f of 2. Well, when x is 2, y is 5. So this is 5. F of -5. That's funny. I have a feeling, I'll double check this, but this is, does it actually have a point at -5? Because it is open. There is no point there. It approaches -3, because if we ask for -4.9, we can give an approximate point, but exactly at -5, D and E. We know what D and E stands for? Does not exist. It does not exist, or no solution, no point there. It's open. Find all values for which f of x is equal to 0, where y is 0. Well, there's 2 at -4 and 4. When x is -4 and when x is 4, we do have a y value of 0. They both work. Find all values of x where f is equal to 3. F of x equals 3. I really hope you're not going to try to list those out. Because the numbers of numbers that we have between those is infinite. So we're really talking about the interval from -3 to 1. All the numbers between -3 and 1 work for this here. Determine the x-intercepts. We already did, -4 and 4. The y-intercept is 3. We're across the y-axis. The domain. All the x values that are included, it starts off at what? -5. So we'd have a parentheses -5, comma, infinity, because it continues on to the right. For the range, the biggest y value that we have is 5. The smallest we have is -infinity, because this is the top and it continues on indefinitely. We know it will because of the arrow. But that's it. Hopefully this isn't anything new. There's a rehashing of everything we've done so far, but that's it. So 1, 7, 2, 1, and 2, 3. So assignments, get those done by midnight Sunday. And that is it.